So I think we can start. So Dirk Hofmann from Aveiro will speak about Barr-coexactness for representable spaces.
Thank you. I hope you can understand me, at least acoustically. As we will see. First I would want to mention what I was talking about is joint work with Pedro Nora, my former PhD student, and with Marco Appardini. And what I want to tell you today is that there's a certain category of spaces, that the duality has an algebraic flavor. Of course, I could just tell you that that's why I'm going to talk, but you are not that lucky, because the category I want to consider, the spaces probably you have never heard about. I would first like to put it in some context in the way why we are interested in that. And in order to explain this, let me recall something very classic, which you certainly all know, the duality theory of Stone. So the category of Boolean spaces, which are certain compact Hausdorff spaces, is dually equivalent to the category of Boolean algebras. Now, at more or less the same time, Stone also provided a representation theorem for distributive lattices, and more concretely, he shows that the category of spectral spaces, that are certain topological spaces in certain continuous maps, is dually equivalent to the category of distributive lattices. Now, this is the result from 1938, and maybe also because the spectral spaces are not very familiar in topology. There is a second version of this result due to Hilary Priestley from the 70s, where she substituted spectral spaces by what we call today Priestley spaces. Now, if you don't know what this is, these are certain Klopen-separated ordered compact Hausdorff spaces, and this refers to the category of ordered compact Hausdorff spaces introduced by Nachbin in the 50s. And these are compact Hausdorff spaces equipped with an order relation, which are somehow compatible, meaning here that the order relation is closed in the compact Hausdorff topology product. Well, but for us, maybe here the bottom line is that these two categories of spaces, Stone spaces and Priestley spaces with dual losses, are exact categories, are varieties. And this created for us the question, what about their parent categories? What about compact Hausdorff spaces and what about ordered compact Hausdorff spaces? And for compact Hausdorff spaces, this is very well known and very long known, which I will call on the next slide. The dual of the category of compact Hausdorff spaces is actually a variety, and hence exact. This was proven, or at least announced, by Daskin in 1969. And the result essentially uses some, it's not very difficult, uses some topological properties, especially Oreson's lemma. Maybe a bit more about this. What is next? It's not a finitary variety, because the unit interval is under 1% but not finitely presentable, and hence it cannot be a finitely variety. Now, that's an abstract result. What about the algebraic theory? Can we say something about this? And this was at least described regarding the operation by Isbell in 1982, who described the algebraic theory of the dual compact Hausdorff spaces and showed that it can be generated by 5 operations. 4 of them are finitary, and 1 is countable arbitrary. He doesn't say anything about the equations which characterize this theory, and this was maybe somehow surprisingly only recently described in a paper of Vincenzo Macca and Luccareccio. They described the algebraic theory of the dual compact Hausdorff spaces also by a finite axiom. Okay, said about compact Hausdorff spaces, and we were wondering about the ordered compact Hausdorff spaces, and in this case we didn't find much in the literature, except that I presented here that Nachbin itself in this book provided enough analogs to topological results which allowed us at least to conclude immediately that the unit interval is injective and is a cogenerator with respect to substance syntactics. that essentially again is due to an ordered version of the Ursum we provided. As well, with a little bit of work, one could also deduce that embedding means regular mono and surjection means AP, which helped us then eventually to conclude that the category, the dual of the category of partially ordered compact Hausdorff spaces is a quasi-variety. This essentially engaged in the book of Nachbin. It's not finitary, it's counter-variety. So, of course, in a later paper we could characterize the finite and co-presentable object, which are precisely the finite ones, and also the binary co-presentable object, which are the traceable ones. Here I should explain, it doesn't need to be a classical matrix, it's a matrix in this extended matrix in the sense of Navier. And it means that the order relation is induced by this matrix, and the topology is induced by the symmetrization of this matrix. So it's slightly different from the compact Hausdorff case. But it still left the question open if it is a variety, so if it is an exact category, which we couldn't prove. But fortunately, Marco Abadini and also Luca Recchio finally proves that Postcomp is an exact category. And Marco gave the first proof based on MV algebras, and later in a joint paper with Luca Recchio, they had a more difficult proof of this fact. Okay, so we know that the dual of partially ordered compact Hausdorff spaces is a variety. Now we are wondering how the dual category of it looks like. There are, of course, several approaches. What I want to tell you, of course, here is our approach. And again, I return first to classic pre-state duality, which can be seen a functor going from the opposite of pre-state spaces to distributed lattices is contravariant Hom functor into 2 lifted to distributed lattices. But somehow to develop duality theory, it was more useful to think a bit more general and enlarge morphisms. Here is already on that side. And instead of considering pre-space spaces and functions, we consider pre-space spaces in certain monotone relations, so categorical terms that are essentially distributed, which also must be continuous. And since we enlarge on this side of morphisms, we also have enlarged them here, and instead of considering maps which preserve all finite and all finite soups, we consider maps which preserve just finite soups. Okay, so that's also already classic. Normal functor here, instead of taking maps into 2, we can also think it takes relations into 1, which is essentially the same. Now for partially ordered compact spaces, we want to do now the same. So on the left-hand side, we consider now partially ordered compact spaces and again distributors, continuous distributors, and we should put some category here, which I didn't specify yet, because in order to get right here, we should again look here and think the distributed lattices are in particular special ordered sets. So we can think here that the special ordered sets, that is categories enriched in the quantale, in the Boolean algebra 2. And moreover, distributed lattices are then finitely co-complete, and lattices at first finitely co-complete such categories, and distributivity can be expressed as that it has enough characters. Now if we look here, instead of working with the 2-element quantale, we take enrichment, it will always be quick, we take enrichment in for instance, to describe because only set is in a co-generator. So we would think that instead of categories enriched in 2, we should put categories enriched in 0, 1. That is essentially matrix spaces. And that's what we want to do here. And according to what I wrote here, we would now expect that we take such categories which have all finite limits and all finite weighted co-limits, which is almost what we do. We take finite co-limits, which can be seen as the analogue of what is written here, but instead of finite limits, which somehow didn't work, we had to add an additional multiplication, so we made it a monoid. Here one just would need to observe that the category of finitely co-complete matrix spaces in the enriched cell, I always hit the wrong button, that this is a monoidal category, it has a monoidal structure, and we take monoids with respect to this structure. So a little bit one should think of this category here as the analogon of this category. And in the enriched setting, and we could then prove that at least the functor going from the partially ordered compact spaces and distributors into this category is fully faithful. What is left then is to describe how the image looks like to get an equivalence. And in this case, we could also do that. And essentially, we have to add that we consider now matrix spaces or categories in which the unit interval with powers. We need Cauchy completeness. And in order, we also need some kind of distributivity, that is, we require enough characters into the unit interval. Okay, but I don't want to focus so much on this, on the image of this functor. We have now an equivalence which categories here of relations, and we would want to restrict it to functions. And indeed, that wasn't very difficult. No, not so much. A relation here, or a distributor here, is actually a function precisely on the right-hand side. I think I didn't mention we take here as morphisms, not the morphisms which preserve the monoid structures, but which only actually preserve it. So there's an inequality. But functions on this side correspond then precisely to the morphisms which preserve the monoid structure. And the proof of it, I would like to indicate quickly, because I want later on to refer to it. At first, one can observe that the distributor here, which is essentially a closed subset, corresponds by equivalence to a morphism in this category. And then one can prove that this is actually preserves the monoid structure, precisely if this closed set is irreducible. And that the fact that every partially ordered compact spaces is so allowed to reduce the relation to a function, or the closed subset to a point. I will repeat this argument in a few minutes in a new context. But now, as I mentioned already, the category we wrote here should be an analogon to the category of distributed lattices, except it is not exactly because we have to impose this additional monoid structure instead of just taking related limits. And the reason for this might be that in our translation from order structure to matrix structure, we are not really consequential. We have translated here, we have translated here, but we didn't translate here. We still consider order structure instead of matrix structures of compact Hausdorff spaces. So the next step would be that we also add metric on the left-hand side. So instead of partially ordered compact spaces, we would want to consider metric compact spaces, which I would need to define first. And in order to give the idea, I want to first recall a result which goes back to Flack in 1997, which identified partially ordered compact Hausdorff spaces as algebras for a certain monad on ordered sets, partially ordered sets. So what we would want to do now is to substitute this category by matrix spaces. But the monad isn't really clear how to translate it to the metric context. It's a monad of prime filters on upsets, which is not clear what that would mean for a matrix space. Fortunately, there is, due to Walter Tholen, a slightly better description of partially ordered compact spaces as algebras, which now doesn't use this prime filter of upsets monad, but it does use simply the ultra filter monad. We have to make a little switch here, which I indicated by changing the name of the category. We consider now not a partially ordered set, but just what some people call pre-ordered sets, so we only insist on reflexivity and transitivity. Okay, but now we just have to consider the ultra filter monad. I indicated here how to extend it to ordered sets. The order relation to ultra filters is not just defined like this. For all exists. Now this is relatively easy to translate to matrix spaces. We would define the metric compact Hausdorff spaces as an algebra for the ultra filter monad on matrix spaces. where now we define it on matrix spaces in a very analog way to this one. And actually, we could go right away a step further and not just extend it to matrix spaces, but to categories enriched at least in some quantale, which I think I indicated here. And maybe to explain this, I should just recall, we refer here to the description of Barr as matrix spaces as categories enriched in the unit interval. And since I had a long train ride, I could experiment with making some, that was too quick, some pop-up window here. There it recalls that Barr viewed matrix spaces, or defining axiom of the matrix space as the instance of the choosing the unit and the composition law in the category. And this is, of course, also analogous to view an ordered set as just the identity and the composition law. And in general, we might consider categories enriched in some quantity, where we have a multiplication and a neutral element, and we can express the same properties. And now, based on this, as I indicated here, quantale-enriched Hausdorff spaces we will see as an instance of the ultra-filter monad on such categories enriched in quantale. And since I'm at it now here, I would also want to indicate that when we define free-space space simply, or enriched free-space space as such an enriched compact Hausdorff space which has enough characters, which is similar to the definition in the ordered case. Okay, I think I finished here. And with this notion, we could improve with our results we had before. We could now at first prove that if we take against this enriched this matrix free-space spaces with matrix distributors between them. Now it's almost too quick here. We get a fully placeful factor now in the category which is simply matrix spaces which are finitely complete, have all finite weighted coordinates. And again, we would want to restrict this to maps. So we would want to have on this side, instead of this matrix distributors, maps. And on the other side, now we can see we just have to add weighted limits and preservation of finite weighted limits. So we can restrict this to all maps. If on the right-hand side, we consider now what I wrote matrix finite lattices, which are matrix spaces which have all weighted limits, all weighted colimits, and maps preserve the structures. I indicated a little bit of proof, which is very similar to the one I indicated before, except we have to completely change the context to explain this a bit. So now a distributor here from 1 to x is essentially a map into the unit interval, which now corresponds to such a morphism here, which preserves finite weighted limits. And then in analogy, which happened in the ordered case, we can now prove that such a map is irreducible. I'll explain in a minute what this means. Precisely if this map preserves finite weighted limits. And by irreducible, I mean here that at first we have to define also matrix topological spaces, which actually are the same as what was introduced by Bob Lowe in approach spaces. And for subspaces, we had to define distributors. And then we could show that irreducible means that these distributors are left adjoint. And then soberness in similarity, which Barr described Cauchy complete matrix spaces, means that at the left adjoint irreducible distributors is representable. And then we could show that these matrix compact Hausdorff spaces are indeed so. And sometimes you see it's the same proof, we just have to move the context. What we couldn't do here is to describe the image yet. Essentially because we don't know yet how, for instance, a Stone-Weierstrass theory in this context would look like. So if you solve these questions, let me leave it. Okay, now since we don't really have yet a dual equivalence, that comes now to the question, is the dual of this category, or more general, of matrix compact Hausdorff spaces actually a variety? And that was then the question we considered next. And I think it appears in the next slide. Okay. To make a preparation for this, at first, maybe I refer to a note here at first. I introduced ordered compact Hausdorff spaces at first as compact Hausdorff spaces with an order relation, which is compatible with the compact Hausdorff topology. Now, Nachbin originally expressed this by saying that the order relation is compatible with the topology in the sense that it's closed in the product topology. The description of Walter Toll describes this as that topology is compatible with the order relation, meaning if I think of the compact Hausdorff topology as convergence, then the convergence map must be monotone. Now, and this describes the ordered compact Hausdorff spaces as the algebras for the alpha field. Now, we took this as a starting point to define now in general metric or B-categorical compact Hausdorff spaces, requiring here an algebra map. But again, we can translate it back to the original definition of Nachbin. We just have to observe that our quantale, for instance, on the unit interval, we can put a topology. In the case of the unit interval, it's just the other topology. And then that this is a defunctor, so an algebra structure is equivalent of having that this map is continuous, which is the analogon to being a closed subset. This is a description we use quite frequently. And so maybe just a quick observation, it helped us for any morphism in this category, metric map, which is also continuous, we can define a new metric on the domain, just like I wrote it here, which we can identify as being continuous with respect to the other topology, and is below the original metric of the space X. I will mention it here because this type of matrices describe quotients. More concretely, we have an order isomorphism between such matrices on X and quotients of X. Here by quotients, for now, I simply mean a surjection. And this helped us to deal with certain questions because it was easier to deal with these matrices instead of dealing with surjections, quotients. Okay. Now what we have to prove, for instance, in order to get that this category is dual or it is exact, is that regular APs are full-back stable, for instance. But because we are in the dual, we have to work that the regular monos are push-out stable, and we have to again get that equivalence relations are effective, but again, because we are working in the dual, we have to dualize in that equivalence correlations, I think that's what we should call it, are effective. So in any way, we have to deal also with push-outs, and maybe just to give an impression, we could somehow describe the metric on a push-out in this category, which basically says that the distance of a point from here and the point of here can be approximated, this is infimum says, by points from here. This result was useful to actually get, which at least we needed some time, to identify the epimorphisms in this category as precisely the surjections, and hence also the subspace embeddings as regular monos, which was then useful for full properties. And to make this short now, here's this result I just mentioned, and with a similar description to the diagram I had before, we could now identify that regular monomorphisms are push-out stable, and because of certain completeness and co-completeness properties, in this case were trivial, we could relatively quickly then deduce that the dual of this category is actually a regular category. That was the easier part. And the more difficult part was to get it exact, as it is that equivalence correlations are effective. And okay, maybe here to record, we have to translate everything into the dual category. So we consider now an epimorphism from some space with itself, which we know already is a surjection. And translating the properties of an equivalence relation to the dual means now that we have reflexivity, we have symmetry, and transitivity. And that was then the time that became useful, that we don't have to work with quotients, with projections, we could work with certain matrices, in this case, on the sum of X with itself. Here I just put some notation. The next slide, so we will usually refer to both copies of X with the second component 0 or 1. And if I write a star, it means we switch the two. And as I mentioned already, about such a quotient, we can think of simply such an additional matrix on X plus X. Now, if we want to work with such matrices instead of quotients, we have now to translate these three properties into properties of this additional matrix. And accordingly, on the next slide, I will have three lemmas which do this. Maybe go quickly over it. The first symmetry in terms of this matrix, symmetry, reflexivity, just means this inequality when we compare with the original matrix on X. Symmetry will essentially just mean in switch, and fortunately also the transitivity we can express is that the distance with respect to this matrix can be approximated using also the matrix combination with points from X, and then again always switching the side of the cofactor. Now this way we could describe in terms of such a matrix what is an equivalence correlation. In order to prove exactness, it would be also useful, or was useful, that we can describe what it means to be effective without necessarily already referring to an equalizer. And fortunately we could do this as well. And again, that such equivalence correlations now have, if expressed in terms of such a matrix, is effective, can be expressed as such an equality regarding the matrix. And then using this, we could actually prove that every equivalence correlation is effective. I would like to add here that this was probably the most complicated part, and we need to also do this in SLAM in order to get this approximation which this description here requires. And then again, everything else was relatively easy, and so we could eventually reach to the conclusion that the dual of this metric compact Hausdorff spaces is indeed an algebraic flavor, is an exact category. I don't know how many time is, but zero. I guess that's a good point to stop anything. So, thank you very much for your attention.
Question, some comment?
Is it by chance, sorry I lost in the middle, but is it by chance Burr protomodular?
The honest answer is I don't know.
Okay, we'll
But
discuss
again, we
it.
should look at it, yes.
Other questions? Yes, please.
Yes, so what is left to prove in order for that opposite category to be equivalent to variety of algebras, we need what generation?
Yes, yes. I'm not sure if this category has one. I would expect that we should restrict ourselves to this enriched priestley fixes. And then probably it's a variety. If this category has a co-generator, we don't know. But if it is, it's probably not a unity term. We don't know what it could be.
So, further questions. So let's